I will talk today about some of our work on aligning prediction and decision quality in the context of predictive policing. And what this talk is essentially about is, so you won't see a new fancy machine learning methods in this talk. It's also, I mean, I'm from a business school, so we don't do new fancy machine learning techniques to that extent at least. We are thinking more about, okay, what do I actually do with these, let's say, run-of-the-mill machine learning techniques? Yeah? Or what do I do with these run-of-the-mill predictive techniques when I want to use them? And how sure can I be that when I use a certain technique and base my decisions on the predictions that I get using the technique, how sure can I be that I actually make the right decisions in that sense? As I said, the context is predictive policing. I do this work together with Oliver and Dirk from the University of Freiburg in Germany, basically my alma mater, where I did my PhD. And Maital Zarczykanski from the University of Texas at Austin. And yeah, let's get right into it. So predictive policing, I think, is something that a lot of people here will, have a basic idea of what it means. But I usually like to start this talk by, pointing out the local context of the topic. So last year I gave a talk on this in the San Francisco Bay Area. So I gave a overlook of the crimes surrounding the conference hotel. And in this particular case today, I looked up the crime data that is available for the surrounding of the British Library where we are today. And what we can see is that, especially in the UK, but also in the United States, there is a lot of publicly available crime data. So basically, I'm always interested, how threatened do I need to feel when I go there? So what is my threat to my life? So I always look up, violence and these type of crimes, homicides and whatever. And we see, in January, especially at the train station, there was, on average in the surrounding about 1 violent offense per day. So that's the reason why I only stay for 24 hours here, basically to minimize the chance of getting hurt. But what this illustrates is we do have, all this data nowadays. And I mean, like all the police departments naturally already had this data, of course, on the crimes, on some paper documents and so on. But nowadays it's really publicly available. In Germany, not to that extent yet, but as I said, in the UK, in the US, you can just spend your entire day going through crime statistics with particular geo-coordinates and times and type of crime and so on and so forth. And the question is a bit, what do you actually do with that data? Yeah? So when we talk about predictive policing, it's about using crime data and maybe other types of data to predict future instances of crime, future occurrences, to do something about it. Yeah, so it's relatively unspecific, honestly, because, and I think this is going to be one of the main points I will go into, that a lot of research in predictive policing is going really into the prediction right now, or for the past years, but the step afterwards, what you actually do with the prediction, is still a bit fuzzy. And it's also, if you talk to people who have been doing this research for a few years, it's in a lot of context really unclear, But we will look into that over the next, let's say, 30 minutes. Also, one more thing, basically, I know that on the program is that 45 minutes talk, 15 minutes Q&A. If any questions come up during the talk, just interrupt me. So I usually like to make things clear while I'm talking, and especially, if you don't understand something or an argument that I'm making, just let me know, and I'll try to make everything clearer. Also, the second thing is this is still very much work in progress, so in general, I'm very open to any types of comments. But it also means that for some of the illustrations, we haven't done the high-resolution version of the pictures yet. So forgive me if some of the things still look a bit pixely here and there. So what we worked with in this particular research is crime data for San Francisco over, I think, 3 months. And the reason that we have this particular city and this particular data set is that at the same time we also had Twitter data, like a complete data set of Twitter data, geo-referenced tweets from the same area. And that was a bit how this entire research field for us started. Basically, we were like, oh, we have all this new social media, blah, 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 and we wanted to see how can we use that to basically improve crime prediction, crime explanation, and also, you know, prevention to the in the end. And I think that is already sort of part of the answer to the question, what do I want to use these predictions for, right? So I want to use them in some way to prevent future instances of crime, or to be responsive to crimes, to essentially have these cars, for instance, located relatively closely to wherever I anticipate future crimes to be, so that either they have a preventive effect, so that, you know, the potential criminal sees these cars and is like, oh, I'm not going to do that, or just to, you know, have a very short response time in that sense. We started that work with not prediction, but explanation. And our motivation for starting with explaining crime was that we felt that sort of these new data sources, Google Maps, Twitter, so the point of interest on Google Maps, OpenStreetMaps, and so on, but also social media data, actually bring something new to crime explanation models. So sort of the traditional approach in explaining crime patterns was very census heavy. So for the, I don't know, 30, 40 years before Google Maps came up and Twitter came up, a lot of crime was explained using demographic factors, economic factors, so factors that you usually find in census data. But there are several theories on crime and you know, what determines a criminal act. And one of them has these two, let's say, constructs, criminal readiness and opportunity. So criminal readiness, for instance, determines sort of the state of mind of the criminal. So is it, you know, somebody who is prone to commit a crime, either for, you know, mental reasons or economic reasons, demographic reasons, whatsoever. And the second aspect is opportunity. So is there actually a situation where I can, as a criminal, commit that crime? So if I want to steal, you know, or if I want to rob a bank, I need to be sort of mentally, you know, willing to rob that bank, but there also needs to be a bank. So basically those two dimensions. You always need the opportunity and sort of the readiness in yourself. And what we found is that census more or less, you know, captured this side, but it doesn't really say anything about opportunity, because a lot of census data traditionally is really about the people living in a certain area, and you might get, you know, some information also on the number of businesses and so on in a certain area, but you don't have this fine-grained data on, you know, shops, on banks, on all of these things. So that is basically why we started with the explanatory models to see what additional value Google Maps and Twitter, as, you know, social media, sort of the public presence, how many people are actually around a given area at a given time, and Google Maps for the structural environment, for the again, shops and so on in a given area. And yeah.
I'm sorry, the criminal readiness refers to the individuals, right?
Yes.
So you mean, when you talk about the economic situation, do you refer to the economic situation of individuals which might push them?
Yes.
Okay.
So basically, I mean, as I said, there are several theories when it comes to, you know, crime in general. So it has been researched for decades. There's also this question, you know, do you do, and this is actually one issue with census data. There is this marauder and commuter theory. So there are certain crimes that you do sort of in the area where you live. I mean, domestic violence is basically the most obvious of that. But there are also crimes where you actually go to places where you don't live. So for instance, if you rob a house like of rich people, and you yourself are not rich, then you go to a different area to rob that house. And this is basically one problem with the census data, because the census data either captures, let's say, the economic situation of your target, in a sense. So, you know, do you have rich people living there? Or it captures the economic and socio-demographic data of the people living in a particular area that might commit crimes. So this is not easy, basically, to distinguish those things, and that is also one of the reasons why these explanatory models historically were not that good. I mean, they have a lot of issues also with topics surrounding racial bias and all of these things. But what we actually found is that when we add those two things, explanation becomes much better, simply because it captures a completely different dimension that was not at all in the data before. But as I said, that was basically what we started with. And then we thought, well, you know, it's nice to have a sort of better understanding what drives crimes to a certain extent, so this explanatory component. But at the same time, this whole topic, predictive policing and so on, came up. And that made us start, you know, looking into the topic of prediction. So can we actually use this data, use these novel data sources, social media and so on, to better predict when a certain crime will happen, and hopefully also, you know, provide certain strategies of how to prevent it then in return. And so maybe actually let me ask you, who here is familiar with the topic of predictive policing in general? Okay, so then it's good that I have this particular slide in here, because one thing about predictive policing is the question, how do you measure how good your prediction model is? And actually, we will talk a lot about this today, but one of the sort of general approaches in this context is to construct something that's called a surveillance plot. So it's, in a sense, you know, what you get in the end, it's very similar to a receiver-operator characteristic. So for the surveillance plot, the question is, how many percent of the area do I have to survey, so to cover, essentially, with police cars or whatever, to catch how many percent of crimes? Yeah? So basically, you know, just to give you an example, so I have 3 different areas. So we use tiles because we essentially have a raster grid. So let's say we have 3 tiles. I have 10 crimes overall, 6, 3, and 1. And let's say my prediction works reasonably well, so that my predicted ranking is essentially that the tile with 6 crimes is top, tile with 3 crimes is second, and tile with 1 crime is first. And then basically the surveillance plot, now I need to use this, just shows you that basically if I cover 1/3 of my area according to that ranking, I have covered 60% of the crimes. If I cover 2/3, I have covered 90%. If I cover 100% of my area, then I have covered 100% of the crimes, so that is usually the case. And then basically similar to the RC, you have an area under the curve, and this area under the curve is in context of predictive policing, or let's say a lot of spatial prediction techniques used as a measure for basically how well my prediction works. So this is basically a very simple example. Then for our particular case that I will go into in a few minutes, we have 1,423 tiles, and basically what we can see here, if I, let's say, cover about 10% of the area, I can, you know, I have covered about 60% of the crimes that happen. And we actually see that there's, you know, sort of an equilibrial state, at least for a few percent there. So at least when it comes to that prediction technique, and then it increases afterwards. So with 10% of the area, I can cover 60% of the crimes. And then for the full data set, you know, the curve becomes smoother and smoother in the end. But at the end of the day, I get, again, some area under the curve as sort of my accuracy measure. Just basically on some background, or to provide some background, what I'm talking about when I'm talking about the prediction quality in context of predictive policing. And the second piece of background I want to give relates to previous work. So there's a paper by Matthew Gerber from a few years ago. It was one of the first papers that well, really looked into, you know, what can social media provide me with when I'm doing predictive policing. We also have this surveillance plot and the curve as a result. So what they do is basically their benchmark is I'm just using historical crimes, because of course crimes do have a very strong, let's say, temporal, spatio-temporal repeating pattern. So you also, as a policeman, you usually know, you know, this is an area that is, let's say, risky, this is an area that is fine, and so on. So, and this is, of course, experience, and it's built around the fact that these things occur again and again in, you know, very similar areas. So you have these very strong patterns, which is why, you know, just using the historical crime density already provides them with, let's say, a pretty good prediction. So they find 71% AUC in this particular context. So again, we have the area surveyed compared to the number of incidents captured. And what they add to this historical crime data are features from Twitter. So they actually use LDA to identify, you know, topics in the tweets that are sent, and then they use these topics as features to basically improve their prediction, and they find that, you know, there is some improvement to the prediction. So it increases from 71% to 74%. The thing is, these topics that they find, they don't really argue why this topic in particular should have any relevance, you know, for predicting crime. So again, it was very early work. I mean, 5 years old, so it also shows how quick this area is moving in general. But basically, it was just about showing, okay, we can use social media to improve predictions. The problematic thing, in addition to the fact that there is not really a logical, let's say, link between the topics that they found and the crimes they predicted, the second problematic thing is that their predictions were for the next 24 hours. So basically, all of these measurements are crimes in a city, I think it was Chicago, for the next 24 hours, right? And the critical question that comes up then is, what do you do with predictions for 24 hours? 24 hours when it comes to crimes is, you know, very long in a sense. So what do you do as a police department with a 24-hour prediction? Because when we look at how crime patterns change during the day, we actually see that they change a lot. So here, this is just the temporal dimension. So we see that, for instance, so we have two crimes, assault and theft. And I mean, we see a very strong, let's say, temporal shift. So at night, there isn't really a lot of theft happening. Theft mostly happens during the day. And we also have fewer assaults during the night, but of course the amplitude is much lower than for theft. Yeah, so assault is, let's say, more fixed during the day. There's less variance between these 4-hour blocks. Theft, there's a lot of variance, and this is just the temporal dimension. So if we look at the spatial mapping of those crimes, there are also very, very strong shifts during the day. I mean, in the evening, you will probably, you know, in the pub and bar areas, you will have probably a lot of crimes. During the day, it might be, you know, the other touristy daily things where you have a lot of thefts. So using 24-hour predictions essentially puts this all, you know, on an equal footing in a sense. So it puts it all on an equal basis. and sort of eliminates these temporal shifts and the spatial shifts associated with it, which, you know, again raises the question, what do I do as a police department with this forecast? So I might think, okay, this is very, very likely that I will have a crime in this area, so I send a car there, but of course, you know, I cannot keep the car there for 24 hours if I don't know exactly, basically, in which time this is going to happen. Also, when I'm saying it's very likely that I have a crime there, it still means that it's very unlikely that I have a crime there. So something that we really need to be aware of is that these probabilities we are dealing with here at a particular location, at a particular time, to have, you know, a theft or an assault, the probabilities are very, very low, far below 1%. And so we deal with very, you know, rare occurrences. I'm always saying, you know, as a researcher, it's very hard to work with crime data because there are just so few of them, so few crimes during the day. It would be much easier if there was more crime. Unfortunately, there isn't, and yeah, that leads to, you know, again, the question, what do I do with 24-hour predictions? And our answer to that was first, well, I get rid of the 24-hour prediction. Yeah? So what we do is we start to split the day into, as you can see, 6 4-hour time blocks. And I mean, theoretically, you can go even, let's say, more granular. You can go to 1-hour blocks, to 30-minute blocks, and so on and so forth. But the problem is, of course, your crimes become rarer and rarer the further down you go. And we felt, okay, these 4-hour time blocks actually make sense. And that's sort of our argument, because they sort of reflect, you know, the pattern of the day. So in a certain event. So let's say it's 6 to 10 is sort of the morning time. 10 to 2 p.m. is, you know, noon, pre-noon, early afternoon. Then you have 2 to 6 in the evening is the afternoon, and so on and so forth. And we say, well, these things make sense because these time blocks are very similar. So 3 o'clock is not that different from 5 o'clock is basically our argument. And the second thing is, if you have 4-hour time blocks, you can basically combine any 2 of them and you have an 8-hour shift. So also when you think about, okay, how do police departments plan? You know, an 8-hour shift sounds something that is reasonable. Even a 4-hour shift is something that might be reasonable, and then, you know, people come back into the base and do something else. And what we find if we split the day into these blocks is that really these, you know, Twitter stuff, social media, doesn't really, you know, do anything anymore. Yeah. So that was what we started out with. We have sort of this base prediction, which again just uses the historical crime data. Here we just use the density, the crime density from 1 week ago. And we already have 70% basically area under the curve in that sense. And then if we have from 1 week ago and from 1 day ago, we have 72%. If we have from 1 time slot ago, we go to 73%, and so on and so forth. And then yes, if we add Twitter density in the preceding, let's say, time block, so I want to predict, let's say, for 2 to 6, and then I use the Twitter density from 10 to 2 to predict, because otherwise I cannot predict, obviously, because I need to already have observed the density at that time. I go to 0.755, but the thing is, if I also include points of interest, so again, this structural environment, I go even higher. I go to almost 80%, and then if I include tweets, again, on top of that, I stay at 80%. So essentially, Twitter, in a way, just captures certain things that you can also capture with points of interest. Right? And I think it basically makes sense, because these tweets essentially might just capture where people are at different times. but they usually are at certain places. You know, they from 2 to 6, they might be more likely to be in a cafe or something like this, and tweet about I'm in a cafe, and their tweets are geolocated more around cafes. But if I just include cafes as a point of interest, it just has exactly the same effect. And we also did some more research on the this whole textual information that you have in the tweets. So we did not do the LDA, so the topic analysis on the tweets, because again, the problem with the topic analysis is that the topics really didn't make any sense to explain crime. So what we did instead was sort of a sentiment analysis. So we tried to identify negative emotions, positive emotions, anger, and these kind of words in the tweets, and then build a density surface around those tweets with these emotional words, and that also didn't do anything. So what you really can see is that once you go into these smaller time slots, just looking at the data that you use, it's probably sufficient to just use the historical crime data. And I mean, you can get some addition with the point of interest, but aside from that, there is really not a lot that you can gain from social media, yes?
Just a clarification. For the tweet density, are you using the 4 hours before to predict the 4 hours after?
Yes.
Okay.
Yeah. As I said, so you need to use, let's say, 10 to 14 to predict 14 to 18, because you don't know the tweet density from 14 to 18 yet if you want to predict 14 to 18, right? So you need to have a time delay in there.
So the KDE from 1 week ago will be the same time period to predict 1 week after, right?
Right. So this is the same, exactly the same time period.
Okay.
This is exactly, basically 6 time blocks ago.
Okay.
So 1 day ago, and this is 1 time slot ago. Okay. Right? But of course, so we did not add the t-1 here. We probably should in the in the final version, just to make that clear that it is of course the preceding time slot. POI density does not change in the observation, or we just assume that it does not change. And sentiment feature density is the same as the Twitter density, right? Because it's based on the tweets. All right. So, and now we get essentially to the interesting part. We still have half an hour, so that's good. Because that was all basically, what we did over the last, let's say, for the 1-2 years before we really started to looking into this more prescriptive approach. The question, what do we do with crime predictions for 4-hour intervals? Because we at that time we still wanted to find out, does social media data really add something to this? And our results are, in a sense, not really. It doesn't really add anything that you don't get easier with, for instance, point of interest data. So it might just be a proxy for sort of structural features that you have in the environment. And now we still have the question, we still have, let's say, reasonably good predictions. So, I mean, 80% sounds good. It sounds better than what they had in their other papers with the 71%, but it's a different city, so it's hard to compare these values. But yeah, at the end of the day, again, the question is, what do we do with that? And again, come from a business school, so we do a lot with operations, and sort of the operations researcher would answer, well, you assign cars to these 2 different areas, different locations for each 4-hour slot. And then, your assumption is, well, again, if I have a car, it might sort of prevent crime, it might improve the reaction time to crime, and so on and so forth. And that is basically how even more problems come up. Yeah? And that is sort of the key message of this talk, actually, that if you think about all of these things, predicting, and then what do I do with these predictions, and how do I evaluate all of these things, you just have a sequence of interrelated problems, and you have to be aware of the sequence when you start the entire endeavor, because otherwise it does not make sense. So what we start out with is this, we have the crime data, we do some pre-processing so that we have these density surfaces, because again, crimes are very, very rare. So you need to smoothen it a bit to actually get stuff that you work with. So these are these kernel density estimates. We include POI data, we include tweet data, again, tweet data, not really that relevant. And then we train a prediction model. Yeah, and we train different prediction models. We do some fine-tuning, but again, most of them are just sort of your run-of-the-mill R or Python, actually in this case, Python standard packages for random forest and so on and so forth. We will, I will say a bit more about that in a second. So you have a prediction problem, right? So the first thing is you want to actually find the best prediction, right? And how do you evaluate that? Well, you have your predicted, density estimate, and according to that density estimate, you rank all your areas in the city, all your tiles that you have in your raster, and then you do your surveillance plot, right? And then you get like 70%, 75%, 20%, whatever. So this is your prediction evaluation. You have a certain measure for the prediction quality, and then you do this for different methods, different, let's say, parameters to these methods to sort of find your optimal prediction method. But again, this is really just how the sequence of interrelated problems start. The next step is then to actually make a decision based on that. Yeah? So you have your predicted kernel density estimate, you make some decision on how to assign vehicles, so that then for each 4-hour block, you have certain, patrol car assignments. So here, you have an assignment problem, right? And so these type of assignment problems are usually, maximum coverage problems. So you want to specify, or you want to find the locations of vehicles that essentially you cover most of the density surface, so of the probabilities. But again, this is really just one part of the overall thing, because you still don't know how well does your positioning actually work then in practice for the test set. So what you then have is you have a new data set, basically for the same region, and you need to find some measure to assess how well your positioning actually works. Because the thing is, in an ideal world, and again, I'm economist by training, so we talk a lot about field experiments and natural experiments and so on. So what you would actually want to do is, for each prediction technique and each possible sort of assignment technique, you want to do sort of a 3-month field test or something like this, and compare this to another, let's say, police department that did not use these this particular methods or combination of methods, and then you do this for every possible combination of methods, and in the end, this is your perfect combination of methods, and you have to use this 3 months or 1 year or whatever field experiment for each of them, and then 20 years later, okay, this is the one that in practice has worked best. It's obvious why that is practically not possible. Yeah, so we cannot compare all of these possible options in field experiments. So we need to find a way to evaluate how our positioning actually works. And that is basically what we did in this study. So for each of these problems, we tried different things, and we found out that essentially what performs well here does not necessarily perform well here or perform best here. And that is basically the key message again. So you have to, essentially, this should not be your training error and your sort of training cycle that you have, but instead actually this should be the training cycle that you have. So if we look again at these problems, we have 3, right? How do we predict in this particular paper, in this particular project? We use, again, several sort of run-of-the-mill methods. One thing is sort of our very naive benchmarks. We just randomly assign probabilities. Yeah, so each cell gets a random probability just to show, are we, smarter than a monkey? Second thing is, standard regression using this historical data set, so historical crime data, and basically just building a regression out of it to predict future crimes. And then we use a random forest and boosted gradient with different configurations to fine-tune the methods. How do we assign? Again, we use maximum coverage, as I mentioned a few minutes ago. But here again is the question, when is something covered? Yeah? So imagine you have this map of San Francisco. You have 1,423 tiles, so let's say 40 times 35 or something like this, grid 40 times 35 tiles. And for each tile you have a probability, and if you send a car to that tile, you treat as covered. The question is, do you only treat that particular tile as covered? Because, of course, if I have a car in that tile, it will also have an effect on the surrounding tiles, right? And because we smoothed everything in our analysis, it also means that if I have a very high crime probability in tile X, I probably have also a reasonably high crime probability in the neighboring tiles. Yeah? So if I just go sort of from top to bottom according to probabilities, then I will place every car essentially in the same region, because sort of the peak probability is pretty much downtown San Francisco for all of these things. And of course, that is not really what I want to do. I don't want to send all my cars to downtown San Francisco. So what we do actually is we say, well, we still assume that the tile where I send the car to is covered, but also the surrounding tiles are covered by half. Yeah, so we say, okay, half of that probability in the surrounding tiles and the neighboring adjacent tiles is covered. And then if the probability of a crime in that region is so high that it's basically even twice as high as in any other area, then I still send a second car basically into that region, because that also means, it's by far, more likely for something to happen there. But it's still something, so this is still an aspect we are working on, because it's difficult to actually find a reasonably well-working coverage approach there. Because the third question is, how do we actually evaluate in the end how well our prediction method works, or our assignment, basically the combination of assignment and prediction works? And we think there are basically two approaches that you can take. One is for each crime that actually happens in a given 4-hour block, you compute the distance to the closest police car, and then basically compute the average distance. And you want to minimize the distance, because that essentially means, well, you minimize the average distance, so you maximize in a way, you also minimize the response time. Yeah, so if your cars are very close to a crime when it happens on average, they can respond very quickly. That is sort of the assumption there. The second thing is, or the second approach that we take is sort of a binary approach. So we say, if a crime happens within a certain radius of a car, we treat that crime as covered. And if it's not in that radius, it's a 0. Yeah? So it's basically binary. And we look at different radii from 500 meter, 1,000 meter, 1,500 meters, and so on. And this question actually becomes very important. What is really your success measure at the end of the day? Again, we cannot do the field experiment just to see how well or how much our crime incidence is reduced in the area. So it's sort of the proxy we have to work with. What do we find? So first, to give you an overview of the data we work with, we have again 3 months, 3,353 assault crimes, 10,500 thefts in San Francisco. Again, this is not yet the, let's say, perfectly nice illustration we have here. But basically you can see, downtown San Francisco is pretty high for both incidents. But then you have a few hotspots in other areas for thefts, even, further away from the downtown area. And you do have some incidents everywhere, yeah? So across the entire area of the city. So you still, it's much lower than here in the downtown area, but all of this, I don't know how well it can actually be seen. All of this is also, this light blue color. And what we do, just, to summarize this again, so we use 1 month to train our model, 1 month to sort of determine the, what is the best model in the end? What model do we want to use? And then, also for the assignment, we have the 3rd month where we, evaluate how well each model plus assignment method performs. And we did 2 different runs, or not 2 different runs, that's all, but we sort of had 2 different parts to this study. Again, the first one was with average distance, and I have all of these information here because, the symbols are a bit different, and we haven't brought everything together in a sort of holistic manner yet. Again, this is relatively current work. But what we can see basically here is we have our area under the curve, so our prediction quality on the horizontal axis. We have our evaluation score on the vertical axis. And what you would actually want is, oh, it's not in there. You would want to expect a relationship that looks like this. Yeah? With a higher prediction score, your evaluation score goes down. Yeah? So it's not, like normal, you have something that increases, but it's the other way around because, a lower evaluation score when we talk about average distance is better. So you want to be closer to your crimes. And what we can see is, things are all over the place. So we have certain things, certain methods that work very well with respect to the prediction quality, but are not that great when it comes to the evaluation score. And we have other methods that are, let's say, 10% worse when it comes to predicting. But if we allocate our vehicles based on that prediction, they perform very well. Yeah? And the sort of thing to be aware of here is this is the case with 4 vehicles. So and this is, of course, a critical question. Yeah? How many vehicles can I actually assign? And this is also the reason why all of these distances are relatively high, because if I just have 4 vehicles, I don't have, that many options. If we look here at the second panel, there we have 200 vehicles for 1,400 something tiles. So basically in every 7th tile, we can theoretically put a vehicle. And of course, then our distance becomes much smaller, but we still sort of see that it's still not necessarily the best to take the best prediction technique and use it to determine your allocation, because it will not necessarily result in the best sort of evaluation score there. And of course, 200 vehicles is sort of just to demonstrate the extreme case. Yeah? I mean, if you have 200 vehicles for 1,400 tiles, the best thing is probably just to randomly put them into tiles, yeah? Because it's let's say a very extreme case. But essentially, we see we also computed it for a few other numbers in this interval 4 to 200, and we still see the same patterns. Essentially, that decision quality and prediction quality are simply 2 very different things in the end. If we do this for thefts, same thing. Yeah, for 4 vehicles, we again have some methods that perform really well. When it comes to, we have some methods that perform really well for the prediction. But actually, if we used the other methods that performed, let's say, 5% less good in the prediction, we have an evaluation score that is, let's say, 200 meter closer on average to crimes. And of course, 200 meter over 2,500 is 10%. So this is quite a sizable difference. And if you think, okay, response time every second matters to a certain extent. So this is, a relevant difference. The thing, though, is that things are again different when we use different evaluation metric. Yeah. So in our second part of the study, we use this binary assessment. So here 500, so 500 meters. If I have a car within 500 meters of a crime, I treat it as, covered, as responded to or whatever. If not, then not. So here again, what we would actually expect is in this case really, from bottom left to top right, so that a higher prediction quality leads to a higher decision quality. And we see, things are good. Yeah. So at least things are more in line with what you would expect, so that prediction quality and decision quality actually correlates quite well. But what we can also see is that you have, so you have your base estimate, and you cannot see it very well, but it's actually the plus is up here. So just again using sort of your normal regression with historical crime data is one of the best methods across both metrics in this particular case, which again shows that when it comes to crime, really a lot of information is just in the crime data itself, and it's not really that surprising because the sort of actual incidence of crimes captures all of the determinants of crimes to a certain extent, and there is not really that much volatility around it. So here in this particular study, we used 5 vehicles here. We then used 25 vehicles here. Of course, again, with 25 vehicles, our evaluation score gets much better because, it's much more likely that you have a vehicle within 500 meters of a crime. But here as well, we see that the base prediction with just the historical crime data is really, in the top right of our study. But we also see that, again, some methods perform equally well, or maybe even, 0.01% better. So it's probably not really a meaningful difference, even though they have a lower prediction score here. If we look at the theft data, it's essentially the same thing. So there is the crime, just the historical crime data is not as good as some other methods, but we still see that for this metric, prediction quality and decision quality are much more aligned than for the metric we used first. And we see it here as well. Although with 25 vehicles, we again start to see some difference. Yeah. So up here, everything was in line, but we also have very low scores simply because we just have 5 vehicles. But for 25 vehicles, we have some methods, the boosted gradient methods mostly, that perform really well on the prediction quality, but the random forest methods perform much better on our actual evaluation metric. Yeah. So we again see this need to perceive these things essentially in a holistic manner. So to really think about in the beginning, what do I actually want to achieve? What do I actually want to optimize or to improve using my prediction? And then essentially go through the entire cycle to find the best methods in the end. If we essentially map this distance or the performance of these methods with increasing distances. So again, here we have 500 meters, but we calculated it for, I think even not 1 meter, but I think 10 meter intervals for the entire range from 0 to 5,000 meters. We have sort of the random assignment of vehicles, to compare to, and of course, the further I go out, the better random becomes, because random just throws 5 or 25 vehicles somewhere on the map, and then your expectation is that, if your radius is 5,000 meters, it will randomly throw it on the map, so everything is covered to a certain extent, or almost everything. So we almost get to 1 up here. But what we can see is essentially that the base case, so the case with just the historical crime data, works really well, for 5 vehicles up to let's say 1,000 meters. If I have a 1,000 meter radius with 25 vehicles, it's a bit less. It's, let's say, the best method up to 700, 800 meters. And after that, random forest becomes better. Because, of course, the base method historically or looks at the historical crime hotspots and focuses very much on these hotspots. And as soon as I sort of relax my distance measure a little bit, then not just these hotspots are relevant anymore, because yeah, I also have areas that are a bit further out. So we see basically how, depending on, again, my evaluation metric, different methods outperform each other. And basically, we have the same phenomenon for theft. So there things are, you know, a bit further to the left. So where random forest becomes better than the base estimate. But it's the same story, essentially. So the historical data is very good if I essentially just want to find historical crime hotspots. It should not be too surprising. And then random forest becomes, let's say, more relevant if I want to have sort of a more holistic perspective, so on a larger area. So what do we learn from this? And I think we're actually doing pretty well with the time. So obviously, and I think that was sort of what I started with, prediction problems don't exist in a vacuum. Yeah? So you always have to think about what do I actually want to do with the prediction, and we call this, you know, in our management speak, prescription by design. Yeah? So basically, when you do, or for most prediction problems, you have to think about what do I want to do with this in the end. So what decision do I want to support? What recommendation do I want to give in the end? Because these things have a fundamental impact on which prediction method you actually want to use. What we see here with these complex problems where I have many interrelated problems, you know, assignment problem, prediction problem, evaluation problem, we don't necessarily have this alignment between prediction quality and decision quality in our results. So the question is, what do we want to use the predictions for? And something that we have to think about is really sort of these constraints that I work with. So, and how they relate to my prediction, to my decision. So for instance, the key constraint in our problem is that I just have a certain number of available vehicles. So the essentially part of the let's say prediction spectrum. So do I want to predict, you know, the top 2% of tiles? Do I want to really predict well the top 5%, the top 10%, and everything else doesn't really matter? That really matters in this case. So that really matters. How many vehicles do I actually have to assign in this particular case? Because if I just have one vehicle to assign, I just want to find the hotspot. Yeah? And I can get that by just looking at the map, essentially. If I have 20 vehicles to assign, well, I still want to find the hotspot, but I also want, you know, reasonably good estimates of, let's say, more the medium criminal areas. And of course, there are several problems also with, you know, the data set that we have, but they don't really change the, you know, implications of it all. Of course, we have confounding variables in this data set that we do not address because we cannot address them. Yeah? So these crimes that we have here, they are already the result of some vehicle allocation in the city of San Francisco. So there were patrol cars driving around at that time in the city. And we have no idea where, because honestly, I don't think this is being recorded. But even if it is, it's probably not something that police departments would be also willing to share with the general public. Because, of course, if I can just check on my app where a patrol car is currently, then let's say if I would be criminally inclined, this would be very helpful. So this is, of course, something that affects sort of the underlying data set, but not really the results that we find to that extent. And with that, I thought I had a thank you slide, but apparently not, so I thank you very much for, again, inviting me and for your attention, and I'm open to any questions you may have.
Hi, thank you. What is the size of your tiles?
200 by 200, I think.
Meters. Okay.
Yeah.
Yeah.
So, I mean, this is also always sort of a decision you have to make. How granular do you want to make it? And of course, it also has an effect on the question, or on the question of this coverage problem. So if I have 50 by 50 meter tiles, then of course, if I send a car to one of these tiles, it has an effect not just on the neighboring, but let's say on the second and third neighboring as well. But yeah, so I'm pretty sure we use 200 by 200, but I would actually have to double check that. But something in that range, definitely.
Okay, thank you.
No.
So I saw you use point of interest data as part of the analysis. I was wondering, is location and density of point of interest per area the only data you look at, or do you look at of other features of the points of interest, like popularity, how much they are visited, or type?
We don't have the popularity data yet. No, that's really certainly something that can be added. But also, this popularity data has become available really over the last, let's say, year. I would even say, at least from what I'm aware of, that you can really collect it from sources. Yeah. So we did start the project, I don't know, 3-4 years ago, where it simply wasn't available, but it's certainly something that makes sense to look into, whether this might even, you know, improve these things even further, especially I think for crimes like theft, because I think theft is something that you want to do, you know, in a crowd. I'm not a thief, so I cannot say for sure, but I think, you know, in a crowd it's usually easier. So if places are very popular, and you can better differentiate amongst your points of interest, I can absolutely see how that improves your prediction.
Makes sense. Thank you.
Yeah.
Thanks. I'm just wondering, have you compared the different crime types? Because it's obvious that the predictable results will be better for assaults than theft, because assault is kind of the expressive crime. So if you're dealing with the cards, it's obvious dealing with a street crime. So theft, some of the time, not on the street. So it's kind of the property crime.
Yeah. I mean, so the theft data we work with is actually, you know, theft from a person in the sense. So there are different types, you know, burglary and all of these things that are technically also thefts, but called differently. We did look, so we trained different models for assault, for theft, simply because there will be different drivers and different, you know, features will have a different effect for each of these crime things. And of course, a long-term question also for the police departments is, if I have, let's say, a certain allocation for police cars to combat assault and a certain allocation for police cars to combat theft, how do I bring them together? Because of course I usually want to combat all crime. But so we looked at different crimes, and we used those two that we have here sort of for illustrative purposes for 2 reasons. Because, well, the results were the nicest. That is, of course, one of the reasons. But the results were the nicest because they are the largest groups of crimes. So I don't have it in here, but so it was theft with 10,000 something. Then it was other crimes, so all different crimes that don't have their own category. And of course, you cannot do anything with that because it's too heterogeneous with respect to the drivers. And then it was already assault with 3,000, and then it continued with like 1,500 and so on. And if you have 500 crimes of anything over a 3-month period over a city of the size of San Francisco, you really run into trouble, you know, if you split it then into 4-hour intervals, that you simply have too little data. But when we did the explanatory work, we actually did look at some of the other crimes, because there we didn't need to split everything, right? We just wanted to look at you know, what explains these types of crimes. And what we found actually made a lot of sense. So one thing that we found is, well, we can explain those 2 crimes also very well, but what you, for instance, can't explain is homicides, because they are, let's say, crimes of, I don't know what you call it in English, but effect is it effect? So sort of, if, you know, you do it on the spot a lot of times. I mean, there's also premeditated murder, but I think there's also a lot of sort of, you know, you just get angry and kill somebody. I mean, who hasn't done it? and the and I mean there were I think seven homicides or something like this in our data set, so it was a really low number. But what was really interesting is that we could not at all explain driving under the influence, which is also pretty clear because driving under the influence, the crime is recorded wherever that car is being stopped. And of course, it's all over the city in a sense. So it's basically random over the city, and you cannot allocate or you cannot link a particular driver under influence to a particular bar or something like this, where that influence was received. So we did look at different types of crimes, but these were definitely the ones that are, let's say, most predictable and also explainable, simply because also the number of incidents is the largest. Yeah.
I have a question regarding the racial bias that is obviously something that holds back predictive policing a lot. And I mean, we hear about racial bias in individual cases a lot when, like, for instance, the algorithm tells you to just stop and search people of color. In the more tile approach that you follow, or any let's say area approach, wouldn't you have the same problem that basically your algorithm just tells you to put all the police cars into black neighborhoods, for instance?
That is definitely an issue. Yeah, yeah. I mean I mean we had this chat last night about that. So you just asked that question because I told you last night that this is an issue. Now, I mean, this is obvious an issue with predictive policing, and this is actually so. But it's good that you mention it, because some people might think, well, you know, we have these interrelated problems, so why don't we just use a method that, you know, links all these problems in one and basically gives you the perfect allocation directly without going through the step of prediction. Right, so something like reinforcement learning and these kind of things, where you can essentially learn the optimal strategy instead of going through the prediction. But I think in this particular context, and exactly for the reason that you mentioned, going through the prediction step, going also, you know, or doing the explanatory work as well, is really important, so that you actually understand why the algorithm gives you the result you get in the end. Because here, you can, I mean, for the OLS regression, essentially, so for the regression, it's really easy to sort of see the impact of different features. I mean, also if you include census data and these kind of things into your data set, it becomes even, let's say, more comprehensive, and it gives you a way to understand, you know, how, to which degree these results are driven by, let's say, socio-economic indicators and sort of more structural things. So that is definitely one of the reasons also why we don't recommend to use these sort of integrated approaches, so where you don't really get an understanding of why certain results are produced. But I mean, you still need sort of an integrated approach, as we suggested, sort of, you know, this holistic approach that you need to look at your eventual evaluation metric.
Yeah, thank you for the talk. So I have two kind of related questions. One is concerning, have you plotted the errors of like the like between your prediction and your real situation? And second, have you spoken with, like, for example, with the police enforcement to see if does give insights, additional insights to like the existing methods they use that can improve them, rather than using it directly in the assignment problem, but does it give actually insights, maybe with these error plots or so on?
Yeah.
Yep.
So we actually haven't done the error plots simply because it's, I mean, there's so much error in the end. Because of course, for, I mean, again, you have the issue with that crimes are so rare, in a sense, so that, you know, really just plotting the prediction error doesn't really. I think, yeah, I mean, especially plotting it doesn't. I wouldn't expect it to provide that much additional insight, but I think we might just still do it to sort of see, you know, whether we sort of have a bias or something like in there that we are missing. Regarding the police department, I mean, that is something that we really would like to have more interaction there. So I mean, we are trying to reach out. We had a few conversations also with people in projects that are working with police departments. But I think also there really the understanding of what these predictive policing systems are really good for in the end is still, let's say, very, very nascent. So I mean, they have been starting for the past 5 years or so to work with this. So I think the experience there is not that large. But what we would actually be really interested in would be what is actually their evaluation metric, right? Because we essentially, we looked at sort of, let's say, literature on this topic of, police assignment and these kind of things, but it wasn't really a topic before this entire predictive policing thing came up, because there simply was no data that it was really relevant to that extent. And then I think, like, historically, a lot of that has been done by gut feeling, in a sense, and sort of the experience, this is a bad neighborhood, this is a good neighborhood, and so on. But this is definitely something that we would want to do, and any context anybody can provide in this context is really appreciated, because, yeah, I think this is definitely a problem that requires a lot of sort of practical insight, and also, I think to have this conversation is also very important, also for the police departments that buy these things. Because, I mean, there are several, let's say, for-profit predictive policing suppliers like that provide, tools to do this. And I think it would be really interesting to see actually what, police departments use them for, and basically whether they think about sort of this overall impact in that context.
Yeah, just picking up on that, so how do you actually, in the experience that you've had, how do you talk about this with police departments or with government? Because that's kind of the challenge you're going to face with policy, is that you're interested in testing this in the real world to see whether it's right and what other insights it can give, and whether it might actually be like a kind of 50% accurate model, but you want to know that for definite. Whereas for policy, it's much more likely to be that they would like this to be a ready-made model, and they want to test then what the real-world impact is to show that it works. Yeah. So how do you kind of balance those two?
It's a struggle. I mean, it is obviously a problem, and we haven't been successful yet in really opening that conversation with these departments. Also because, so in our experience, I mean, as I said, we've reached out to a couple of them, but they have like, 1 or 2 people who have the great job of, implementing this new system in their agency, and then they are basically loaded with work. And we found a lot of sort of hesitancy when trying to start this conversation. Also because, and I mean, this is again sort of this management angle. You are a police department that just, has bought an expensive predictive policing tool. How much do you want this evaluated when, researchers come to you and tell you, well, we're not sure whether you're actually doing it right? Right? And of course, I mean, we should not go there and say, well, we're not sure you're doing it right. But I mean, there's always this sort of issue that you basically want to confirm that the decision you made is right. And I think that has been part of the issue we are facing when reaching out to these departments. But as I said, in case anybody has, let's say, closer contacts there, we would be terrific if we could actually use them. Because that is, I mean, that is really sort of the one of the key questions that we are still not able to answer.
Could I ask you about how your prediction quality is defined? If I understand correctly, it's based on tiles, right? So it's like the number of tiles covered and the number of crimes in those tiles. So I think that might be why when you do like the binary evaluation, you kind of get more closer to what you expect than with the distance-based one, because your prediction quality is basically binary-ish
Yeah,
because
I
it's
mean,
tile-based.
yes, absolutely. Yeah.
And the other thing was, for the Twitter data, do you you only look at tweets in that tile? So it's like quantity of tweets in that tile and the sentiment of those tweets, if I'm right.
Well,
That's
it's a density, so it actually includes the inverse. I
Okay.
think it's like a 500-meter radius.
But I was going to wonder whether you tried looking at tweets that concern the area rather than in that area. So, for example, if you have like
Yeah.
a big stadium or something and there's some event on in that evening, you've probably got lots of people talking about that area that are not in the area yet.
No.
So you might get some information that way. Yeah.
Let me start with the second question, because that is actually a very similar, thought that I had, or to one I had a couple of days ago. Why, or that we should definitely do that. But then I was thinking, if I analyze my tweets and sort of try to identify events in my tweets, which is always, not easy, especially, if you want to use a prediction, you need to sort of know in advance what kind of event you're looking for. So you cannot really use the name of the event unless it's sort of a recurring sports event. And so I sort of had a circular thought on that. So I thought, okay, maybe tweets is actually not the right approach there, and instead you just use event data. I mean, you have like event data on what stuff is happening in a city, from like large-scale sports events to smaller, concerts in some pub or something like that. So this is definitely something that, for the purpose of predictive policing, really makes a lot of sense to further add to that. And I think this even makes more sense than adding social media in this context.
I guess, I mean, it'd be stupid, but the exception might be if you have a tweet where someone's actually saying, I'm going to rob this place tonight, and then...
Yeah, the thing is that you capture that tweet is very unlikely as well. And there's one tweet where that happens basically once a year or so. But actually, coming back to your first question, I mean, this is basically the problem, right? That you have different evaluation metrics or different metrics you work with in each stage, but there is not really. So we were thinking a lot about this, and we have not found a way how to essentially put the predictive problem, the assignment problem, and the evaluation problem all on, let's say, the exact same metric. Because if you can do that, you won't have that issue. But we think that especially with these kind of urban problems where you simply have a lot of different dimensions, in a lot of cases you have, let's say, very sparse data sets because you try to predict, let's say, phenomena that are relatively rare, especially if you map it sort of both on time and space. Then it's very difficult to bring everything in line in that sense. But I mean, of course, the idea is absolutely correct. Yeah. All right. Well, thank you very much. And again, if you have contacts to police departments who are working with predictive policing systems, tell me. All right. Thank you very much.